Hello and welcome back to Basic Topology, the video series where we learn about topological spaces and what we can do with them. And indeed, in today's part 5, we continue talking about compact sets. In particular, we will show that closed subsets in a compact set are compact again. And this is really helpful because it's much easier to check closeness than compactness. On the other hand, compactness is a really nice property we want to have, as you will see soon. However, as always, before we start with the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And as a reminder, as a Steady supporter, you can download a lot of additional material like books, PDF versions and quizzes. Okay, then without further ado, let's immediately start considering a topological space where, as you know, X is a set and T a collection of subsets of X. And most importantly, these subsets are called the open sets. This means that the starting point is given by open sets, and then we can define a lot of other notions as well. For example, in the last video we have already defined what it means for a subset to be compact. This is a really important definition in topology, so let's quickly recall it. In short, you can just remember it means that every open cover of A has a finite subcover. And the actual meaning of that is if you take open sets Ui and the union of that is a superset of A, then you are able to omit a lot of these open sets and still get the same result. More precisely, you can restrict yourself to finitely many open sets. So this is the explicit meaning of every cover has a finite subcover. And there you might already guess that showing compactness is usually not so easy because you have to consider all possible open covers. But obviously this depends on the topology because sometimes it can be quite easy. For example, the indiscrete topology makes everything simple. And in fact, this one we can write down for any set X. Simply because the only open sets are the empty set and X itself. And because of that, there are not so many possibilities for open covers at all. Indeed, the only set that essentially covers a given subset A is the open set X itself. So because X has to be included in every open cover here on the left hand side, we can just restrict ourselves to X on the right hand side. And with that we have our finite subcover that works for every subset A. So the nice conclusion is that in this topological space, every subset A is compact. Therefore, you should remember compactness always depends on the given topology. And for this reason, it's always nice to have general results that hold in every topological space. In fact, as already mentioned, we don't want to check the definition of compactness all the time, so it would be helpful to know something about subsets of compact sets. So if we already know that A is a compact set, what can we say about a subset of A? In general, such a subset B does not have to be compact again. However, if we have the additional information that B is closed in our topological space, then we also know that B is compact. In other words, for subsets, we only have to check for closeness if we want to show compactness. So this can be really helpful, and in fact, the proof of this claim here is not so complicated. Namely, here we just have to use the fact that the complement of B is open in the topological space. This should not surprise you because this is actually the definition of a closed set in a topological space. So maybe we can visualize that. Here we have our whole space X, and there we have our set B, and everything that is not inside B forms an open set. And here please don't forget that B is a subset of a larger set we called A. This is quite important because now we want to show that B is compact as well. And to do that, we have to cover B with open sets. In general, these could be infinitely many, and then the question is, can we omit some and still cover the whole set B? Here we will call the open sets Ui with an index set I. And then we simply want that the union over the Ui's is a superset for B. So this is an open cover for our set B. And now the question is, can we make it into an open cover for the set A as well? And in fact, this is not hard at all, because the complement of our set B is an open set as well. In other words, we can simply put it to the union to get a new open cover. Namely, this covers the whole space X and therefore also the subset A. So what we get here is an open cover for the set A. And exactly at this point, the power of compactness comes in. The compact set tells us that we can reduce this cover to a finite subcover. Hence we can drop a lot of UI sets until only finitely many are left. And as always, we write that with a finite index set I0. And now the only thing that remains to do is to make this finite subcover into a finite subcover of B. But this is actually already done because A is a superset of B anyway. The only strange thing now is that there is a set included in the finite subcover which was not there in the original open cover. However, because it's the complement of B, we can just drop it completely without changing the cover for the set B at all. So writing it like that is exactly what we wanted. We found our finite subcover. And there we have it. By definition, this shows that B is a compact set. But as you can see, it was needed in the proof that B is a closed set. And this finishes the proof and this video for today. In the next videos, I want to talk more about topological spaces, for example, Hausdorff spaces and locally compact spaces. And there you might already guess that the notion compact plays a crucial role. But all the details about that we will discuss later. So I hope we meet again and have a nice day. Bye bye.